you've checked the voltage, you've checked the current, everything passes and the system's still underperforming. A bypass diode's quietly given up. Shading you can't see from the ground, even something as simple as dirt dragging the whole string down. Basic tests won't find it, but the IV curve will. Every solar panel leaves a signature, not a label, not a serial number, a unique electrical fingerprint that tells you exactly how that panel's behaving when it's healthy and when something's wrong. In this video, we're going to show you how to read that curve, to spot broken panels, diagnose faults, and tell when an array just needs a clean. And with IV curve tracing now built into Sungrow inverters and the iSolarCloud platform, you can do it remotely, straight from your desktop, no climbing on the roof, no waiting for the right weather. So let's understand what an IV curve actually is and why it reveals so much. So what actually is an IV curve? Think of it as a map of everything a solar panel can do. On one axis you've got current, on the other voltage, and the curve shows how those two trade off against each other as the panel operates. Right at the far left of the curve, that's your short circuit current, ISC. The maximum current the panel can produce when the voltage is basically zero. Jump all the way over to the opposite end and that's your open circuit voltage. VOC, circuit's open, no current flows, and the panel builds up its maximum voltage instead. So ISC and VOC, those are the extremes, but neither of them is where useful power happens. The real sweet spot sits in the middle. Right on the bend of the curve, the knee, that's your maximum power point. Defined by VMPP, voltage at maximum power, and IMPP, current at maximum power. Multiply VMPP by IMPP and you get the panel's rated power output, the number printed on the nameplate. That headline figure lives right on that knee. Manufacturers provide these values on the datasheet, measured under standard test conditions. 1000 watts per square meter, 25 degrees cell temperature, controlled lab, and in many cases they'll go further, providing multiple IV curves showing how the panel behaves at different light levels. Not just one curve, a whole family of them, each shifting as the available light changes. But in the real world, it's not just light level that changes. Temperature has a huge influence on how a panel performs. As temperature increases, the voltage drops noticeably. Current changes slightly, but voltage takes the real hit. And because power is voltage multiplied by current, that drop in voltage pulls the overall power down with it. So if you look at the curve, the knee shifts to the left as temperature rises. Lower voltage at maximum power, similar current, less overall power. As temperature falls, the opposite happens. Voltage increases, the curve stretches out to the right, the knee moves with it, and the panel can deliver more power. That's why panels are rated at 25 degrees, but often run far hotter on a roof, and it's why bright, cold days can deliver surprisingly strong performance. Now here's the important bit. All of these effects, light, temperature, the position of that knee, they're not random, they're predictable, repeatable, measurable. Day in, day out, if the conditions are the same, that curve falls in the same place. It's a consistent electrical signature, which means once you know what normal looks like, anything that drifts away from it starts to stand out. Alongside those day-to-day changes, there's something else happening in the background, much slower, but just as important. Degradation. Solar panels are built to last decades. They don't suddenly fail. A good panel doesn't die, it fades. Manufacturers define this in their performance warranties, typically around 1% loss in the first year, then roughly 0.4% per year after that. So over time, that IV curve doesn't suddenly distort, it just shrinks slightly. Same shape, same characteristic knee, just a little less power each year. And that's the key idea. If the curve changes shape dramatically, that's not degradation, that's a fault. Now, everything we've talked about so far has been a single panel, but in reality, panels are connected together to form strings and arrays. So what happens to the IV curve then? The behavior stays the same, the curve keeps its shape. When you connect panels in series, voltages add together, the curve stretches horizontally, current stays the same. When you connect strings in parallel, currents add together, the curve stretches vertically, voltage stays the same, and in most real systems, you get a combination of both. So the curve gets bigger, wider and taller, but the underlying shape and characteristics stay the same. That fingerprint doesn't disappear. It just scales. Of course, the real world doesn't play nicely, because while temperature and light shift the curve in predictable ways, there are plenty of things that don't follow the rules. Take shading, it only takes a shadow across part of one panel, and suddenly the whole string starts to struggle. Then there's physical damage, panels walked on, cells cracked by hail, one weak panel dragging everything else down, dirt-induced issues, dust across the surface, debris collecting at the edges, and of course pigeons leaving their mark. then cabling problems, high resistance joints, water ingress into connectors, sometimes even animals getting involved. All of these problems have one thing in common. They don't just reduce performance, they distort it. They change the way the system behaves electrically, and that shows up not as a simple drop in power, but as a change in the shape of the IV curve. Kinks, steps, flattened sections, a knee that's no longer where it should be, which is why an IV curve trace is like putting a solar array on a lie detector. Doesn't just tell you how much power you're getting, it tells you whether the system is telling the truth about why. And once you know what a healthy curve looks like, those distortions become impossible to ignore. So performing an IV curve trace isn't just interesting, it's incredibly useful. It gives you a way to check that the panels supplied by the manufacturer are actually performing as guaranteed. You can track whether degradation is happening as expected or if something's drifting outside those warranty assumptions. A solar panel underperforming doesn't fix itself, and the client notices the bill before you notice the fault. Left unchecked, these issues don't just sit there quietly, they chip away at performance and ultimately affect the return on investment the client expected from that system. And remember, it only takes one problem panel to drag down the performance of an entire string, which is why we say it all the time. If you can measure it, you can manage it. Now you can perform an IV curve trace using specialized test equipment, and we've actually covered that in a separate video, one you might want to watch after this, where we go deeper into commissioning and the full set of verification tests. But there are a couple of catches. First, you need the right conditions. To get a meaningful IV curve, you need stable weather and decent sunlight, which in our experience is where things start to fall apart, because whenever we turn up to test a solar installation, the weather seems to take it personally. Clear skies disappear and clouds roll in. Now here's where it gets interesting, because there's another way. Using technology built into Sungrow commercial and utility scale inverters, combined with the iSolarCloud platform, you can instruct the inverter to perform its own IV curve trace. No handheld tester, no site visit, and it can all be done remotely. Now, there are a few prerequisites. You still need suitable conditions. It needs to be a reasonably sunny day with stable irradiance above around 500 watts per square meter. The scan also needs to take place within a window around midday, typically within a couple of hours either side, when conditions are most consistent. Once triggered, the scan itself takes around 10 minutes, and importantly, you can set it up to scan multiple arrays at the same time. During that period, the plant won't be producing energy, but in return, you're getting a detailed diagnostic snapshot of performance. There's also one critical setup step. You need to have your strings configured correctly within the inverter, the exact panel specifications, the string layout, because the system is comparing measured performance against what it expects to see. And here's the uncomfortable truth. That level of detail gets skipped on a lot of installations, but without it, you're flying blind. The system can't compare against what it expects to see because it doesn't know what to expect. Now let's look at what this actually gives you. You can generate IV curve reports remotely. Start with a healthy array. You'll see that familiar smooth curve, clean knee, exactly where you'd expect it to be. Now compare that to a different result. If the short circuit current is lower than expected, that could point towards a faulty panel or localized shading affecting part of the string. In another case, the shape of the curve itself might look wrong. The slope is off, the knee is distorted. That can indicate issues like uneven shading, mixed panel types within a string, panels facing different orientations, and sometimes the result is even more obvious: a flat or zero response, which is usually a strong indicator of a disconnected string or a cabling fault somewhere in the system. Now, of course, you can't fix these problems from your desk, but that's not the goal. The goal is knowing exactly where to go and what to look for before you leave the office. So when a maintenance team goes to site, they're not starting blind. They've got a target, they've got context, and they've got a much better chance of finding the issue quickly. That's the shift from turning up blind to turning up informed, from reactive fault finding to targeted intervention. So that's IV curve tracing, from understanding the shape of the curve to using it as a tool to uncover what's really happening inside a solar array. And now with Sungrow inverters and the iSolarCloud platform, it's something you can do remotely, turning what used to be a site visit into a diagnostic from your desk. Same data, same insight, no ladder required. If you want to learn more about the system, we've got a link in the description. And we'd love to hear from you. Drop your fault-finding war stories in the comments. The stranger, the better. And if you want to go deeper into commercial solar, check out the video on screen now, where the Sungrow team joined us in the studio for a proper deep dive into large-scale installations, including how insurance requirements are starting to shape the way systems are specified. Definitely one worth watching.